So in this video, I wanted to go over problem 2.8 of the homework. And what we have is a coplanar force system. We have two forces which are acting on an I hook here. Notice that for both forces, we have the magnitude specified. F1 has a magnitude of 260 pounds, F2 has a magnitude of 310 pounds. And for both, we have sufficient geometric information in order to convert them into rectangular form. Another way to say that is to decompose them into X and Y components, or alternatively, I hat and j hat components. So given all that information, we want to see if we can find an expression for another force, which is denoted as F sub r prime. Usually in the text, when they have F sub r, they're talking about a resultant force. But note that in this case, it is not a resultant force because this force is actually defined as the difference of F1 and F2. So we did talk about a geometrical definition that would allow us to actually compute the difference of those two forces. It was based on the triangle rule. Basically, all that we would need to do is take F2 and use the property of scaling by -1, which would keep the magnitude the same, but would flip the direction by 180 degrees. Then we could do the triangle rule. However, that's not going to be a good approach to do it. In fact, very rarely will we kind of use those geometric approaches. I'm going to use it in the next example, ironically, but generally speaking, we won't. So I apologize. I'm going to turn around and just plug in my computer because, believe it or not, I've had examples in the past where I get about 10 minutes into the video and the computer randomly dies. I have a 2070 Super GPU in this computer because I do some artificial intelligence work on it as well. So with that high power GPU and the high sampling rate monitor, it does tend to die quickly. So I had to be careful. One thing you probably noticed is there's a new folder in our actual course files where I've stored some example homework problems. And in general, I'm going to try to do as many homework problems as I can by hand and kind of show you the solutions, along with provide sample videos when I can as well. When we get a little more advanced in the course, I'm going to kind of adapt based upon the feedback that you provide me. If you tell me you can do a pretty good job of reading the text and actually picking up the theory, and you just want me to do example problems as part of the lectures, I'm happy to do that. Or I can kind of take the same approach that I'm doing now, where we focus heavily on example problems kind of in the week before an exam. So if you notice, the first thing that I did in my solution is I replicated the drawing which I was given. Ideally, even though I don't have a scale drawn here, F1 should have a larger length as represented as an arrow. Then F2 should have a larger length than F1 since the magnitude of F2 is larger. In addition, I've tried to preserve as much geometrical information as I can. So the first step that I'm going to do, since I want to compute the difference of these two vectors, again, remember when you're adding and subtracting vectors, it's very simple if they're actually decomposed into rectangular form. So the question is, how can I decompose F1 into rectangular form? So this isn't an example where we're given an angle. However, we're told that if we were to decompose this force triangle, if we were to decompose the force F1 into a force triangle with kind of orthogonal components, an X component and a Y component, and I haven't actually drawn the vectors in there, but of course, if I did, notice that the F1X would be directed, this would be its tail, and it would be pointing to the left. So its arrow would be pointing to the left, its tip. And in a similar fashion, the Y component of F1 would be pointing in the upward direction. And that's going to be important because it's going to allow us to manually adjust the signs of each of the components based upon that observation. So I'm not given this angle theta. However, I know that how the force F1 decomposes into a force triangle is similar in geometry to this triangle, which I have here, which has kind of a horizontal base of 5, a vertical base of 12, and a hypotenuse, of course, as governed by Pythagorean's theorem, as 13. So what's really nice about this situation is if these two triangles are similar, this geometrical triangle on the right and this decomposed force triangle on the left, then I can determine both this angle along with the trigonometric functions of this angle by just using the simpler triangle that I have on the right. So if this is theta, I know that the cosine of theta, by definition, using the principle of SOHCAHTOA, cosine ka means that the cosine of this angle is equal to the ratio of the adjacent side length. Notice that for this angle, the 5-unit length side is adjacent, divided by the hypotenuse. So cos theta is 5/13. I don't need to know what theta is because really what I want in the majority of these cases is the cosine or sine of those angles. In similar fashion, remember sine theta is the opposite side length divided by the hypotenuse. So it will be the 12/13. And what that allows me to do is actually decompose F1 in terms of the cosine and sine of theta, which I have from over here on the right. So how would I decompose F1? Well, in terms of actually writing its x component, notice that in this force decomposition triangle, the x component is adjacent to theta. So what that means is I'm going to use the cosine of this angle. Notice that in my formula, I've added an additional negative sign. Now, why have I added that negative sign? Well, in general, you can always decompose and find the x component of a force by multiplying the magnitude times the cosine of theta if that angle is referenced from the positive x-axis with a counterclockwise sense. In this case, that's not the angle that we're dealing with. That's kind of a custom theta that we're talking about. It's measured from negative x in the clockwise sense. So whenever we're dealing with this in this situation, what I usually do is I just find kind of the lengths of these side lengths, and I adjust the sides manually. So I know that if I were to write F1 and decompose it into a horizontal and vertical component, the horizontal component would point to the left, the vertical component would point up. So in the natural xy coordinate system, that horizontal component is pointing in the negative x direction. That's why I've added a negative sign in front of my 260 cos theta. Again, the way I look at it is 260 cos theta is just giving me the side length of a triangle. I don't care about whether it's in plus or minus x. However, by observation, I know since it is in the minus x direction, I'm going to add in that negative. I don't have to do that for the vertical component because in our traditional xy coordinate system, the y component, f1y, is going in the positive y direction. How do I actually find what this side length is of my triangle? Well, just whether it's a forced triangle or whether it's just a simple geometric triangle, the rules of SOHCAHTOA still hold. So the sine of this angle is going to be the opposite side length, f1y, divided by the hypotenuse, which is going to allow me to solve for f1y as simply the hypotenuse value times the sine of theta. So 260 sine theta, since we know sine and cosine of theta from over here, just plug those in. What we find is that the x component of f1 is minus 100. Again, it should be negative because if we go back to our original drawing, and this is always a good sanity check to do, f1 should have a negative x component and a positive y component. It does. And if we notice when we do F2, it should also have a negative x component, but also a negative y component as well. So let's actually do the decomposition of F2. Notice that here we're not given kind of similar triangle geometrical information. We're given an angle, which again, unfortunately, isn't measured from the positive x-axis counterclockwise. Now you could say, oh, I can calculate that, Henry. It's just 180 plus 45. And you definitely can. And if you want to use 225, then you don't have to manually adjust these signs with the negative. However, I think it's easier to just find the side lengths of your force triangle and then add in the adjustments as you need. So notice if F2 were to form the hypotenuse of a force triangle with orthogonal bases, then F2x would go out to the left and F2y would go down, which means F2x is going to be in negative x direction, F2y is going to be in negative y direction. Relative to this angle, notice that the x component is adjacent to the 45-degree angle, so I'm going to determine it by using the magnitude, which is 310, times the cos of 45, that's what I have going on here. That negative sign, again, is just to adjust it and note that F2x is pointing to the left. Since the y component is opposite the 45-degree angle, I'm going to use the sine function in this case. Fortunately, this is an impossible one to mess up because sine and cosine of 45 are the same thing. But if you notice, if I'm missing a minus there, but I did grab it back on this, and I'll rescan it to make sure that you're not confused on the actual scan when you look at it. But both the x and the y component are negative. I'm just missing it written there. And one thing I should say that I didn't say earlier, remember that this kind of triangular bracket notation is an alternative to showing the x component weighted by I hat and the y component weighted by j hat. Either one is fine. However, if you're just doing something simple like subtracting, these kind of triangular brackets is probably a good approach because, of course, when you subtract vectors, you subtract the individual components. So notice that in order to determine the x component of fr prime, I take the x component of f1, I subtract away the x component of f2. Be careful, since the x component of f2 was negative, we're going to have a minus minus plus kind of thing. Do the same thing for the y components, and hopefully what you'll find is this expression for fr prime in terms of its x and y component. And if you notice, I carried a lot of precision here because even though the book wants you to report your answers to 3 significant figures, remember that you don't want to do any intermediate rounding or you might not end up with the correct final answer. Of course, if you're using a calculator or a modern scripting language like MATLAB, just store these intermediate calculations and variables and don't even write them out on your paper. So if I have a vector that has this x component and this y component, I can always find its magnitude. Remember, magnitude is just denoted by these absolute value signs. by taking the square root of the sum of the squares of the components. And in that case, if you go through the math and round to 3 sig figs, you'll find that the magnitude of this vector is 474 pounds. And I always think it's a good idea to just draw it out, even though we weren't asked to, if it has a positive x component and a positive y component. And if you notice, the y component has a magnitude that's about 4 times the x component. So it's going to be a lot taller than it is out here to the right. But either way, it's going to be in the first quadrant. And you can see that this angle, right, that I want to report, that I was requested to report, the tangent of that angle is the ratio of the y component to the x component. That's just opposite divided by adjacent, or TOA for the SOHCAHTOA. So since we know FRY and FRX, I can just take the inverse tangent of the y component divided by the x component, carrying around a lot of precision. That turns out to be 75.448 degrees. If you round that to 3 sig figs, it will just be 75.4 degrees. So hopefully that was a pretty easy and review example. If you have two vectors that are kind of coplanar or expressed in 2 dimensions, and you want to do some arithmetic to them, like either adding or subtracting, your best bet is probably to do a decomposition into x and y components. Another name for that is to place them in rectangular form as an initial step.